your thesis as one, if you understand what I mean.
Okay, thank you.
Anything else you want to ask before we start? I make a fish. This is something, it's up to you, but I hope you would return this reports whose deadline is next week or week after that, ASAP. Of course, you have time till mentioned, but it seems that my workload is just coming bigger and bigger. And if you return them at the latest possible time, it may take some time from me to read them. So if you have a possibility to return them earlier, I would be very, very happy. So, for example, the last week topics and this week's topics, curve fitting, basically they require almost nothing to do, so you could easily return them earlier. How about the interpolation, extrapolation? Do you have anything to ask about them? If no, we continue basically the same topic, somehow or anyway a little bit different. So we talk about the curve fitting, interpolation and extrapolation is also curve fitting. So you try to get a function what is always a polynomial function in these cases, and when you have a function, you can approximate the value at given point. If the value is inside the minimum and maximum values of a variable, it's called interpolation, otherwise extrapolation. The function in these cases are always polynomial cases. They may have a power 3, 4, 5, or even 7. So a function could be quite nice. In some cases, you have to take the logarithms so that you can actually use the interpolation or extrapolation cases. But when we talk about the curve fitting in general, the function do not need to be the polynomial case, not even the approximation value function. Although we go through only linear cases in this part, in the theory part, I show you, and there is also part of SPSS. So if you thought you get rid of SPSS already, I am sorry. It actually helps you in here also. The curve fitting here is basically the same kind of case as in the regression. In regression, you should have these numerical variables, and you try to approximate some variable with the others. So you had independent variables, like here we would have the x-axis, and you did have a dependent value which you were trying to approximate. In this two-dimensional case, we do have these measurement points. So, for example, here we have some x value, we have some y value. Although we wouldn't have this red line here, everyone here would see that they are almost going on the line. We draw a line and we see it's not the points are not exactly on the line, but still the line can be seen there. And one of the most common methods for curve fitting is a least squared method. Usually say only LSM. And the idea there is to minimize the difference between this actual value and with the approximation value. If we just take this difference just like that, in this case it would be positive, in this case it would be negative. So if it sum all of them, the result would be or could be 0, and after that we try to minimize the difference. So we actually see whether there is the difference or not by squaring. And yeah,
are you sharing your screen or not?
Yeah, good question. Probably not, if you ask. Does this help?
Yes, now.
Do you want me to start from which point? So here are the measurements, the black dots, and the red line is some kind of approximation. As you see, these are almost on the line, but not exactly. And I was telling you that here the difference is positive, but on the other hand, differences, the result could be 0, although there is differences. They are not exactly on the line. So that's why we have to square all the differences. And when we see that some of them would be something else but 0. Definitely if there is differences. Of course, if they are exactly on the line, then there is no problem. This same kind of case, it's done when you are defining the linear function, but when you only use 2 points. And that kind of idea, when you have lots of measurement points, doesn't work, because the line should be very so good as possible to all points, not only the ones you select. And because we want to minimize these differences, it means that we have to take the derivatives. So the idea behind the least squared method is that the value given by the approximation and the value given by the measurement, the difference of them is as small as possible. So basically, if we have a linear function, polynomial function as an approximation function, the value of this and this, the difference should be as small as possible. So we are derivating this one for multiplier A, and we are derivating this one for multiplier B, and try to find the 0 of those derivatives, because at that point this is minimized. This is also minimized. So if you solve this system of 2 linear equations, you get the functions for A and B separately. this is something you can do by yourself. It's very easy. So formulas look like this. This is just for linear case. If you would have a quadratic case, you would do the same thing, but of course you would have the third case here, and you would solve this system of three equations. So this is how we get these. From this point forward, you can just use these. You don't need to do these calculations, for example, in your assignments, because it's not needed. It's just the idea how to get these. Here we have an example, and these measurements are actual measurements done by our civil engineering students several years ago. There is temperatures given. I don't know which apartment, because they did do measurements for people's home, and they used them as for their practical assignments. So there are temperatures from one house, for example, and then there is the moist, the value of how moist the room air was, and so on. And in this case, as you see, these measurements has been done after every half an hour. And when they were doing it to our home, they did do it for 2 days. So this is only part of the data. And in this case, because this is what I did, the next part, it's not what they did. My idea was that the more the temperature is, the less there is moist in your house. I got these values for multipliers A and B. And when I did take the scatter dot, we already see here that they are quite widely spread. So it looks like that this is not working at all. This is the function it gave me. So as you see, A 1.29 minus 6.33 used here. And I just used the formulas on the previous page. When this one was studied with the SPSS, you see the R score is quite low. So it definitely tells us that this approximation function is not good for this case at all. When I did talk about this one for Petteri, I think you have had some physics courses with Petteri, and also with the civil engineering teachers. They said to me that in your idea there was no sense at all, because there is so many other variables should have been thought also at the same time. But because the data I was given didn't have any other values and variables, I couldn't do it anymore. So as you see, I could have obtained this function also with the SPSS. What I actually would like to show you in SPSS is the part of a curve estimation. This is the data of these employees, and what I'm going to do now, I just select some numerical variables, but I do not have any idea whether this kind of curve fitting has any sense. But that is not the point in this case. It's just to show what you can do. So when you go to the analyze part and you take the regression, what you did do in your statistical reports, you take the linear one. But now you can take also the curve estimation part. So the first one is bit dependent, and I just take the current salary there. And what I try to do, I try to explain it a bit time they have been working there. As you see, there are several models. And because I have no idea what they are, I just select all of them at the same time. And I got this kind of information. It says cubic model could not be fitted due to the near collinearity, so there is no values given to that one. But my main interest is this part. For all these models, I have the R-square here. And as you remember, R-squared said how well the function approximates the values. So from all of these, I select the one with the best approximation. And in this case, it seems to be quadratic. It's no, yeah, it's not good one, but it's the best of these. And then I have all these. It also says here that it is statistically significant because this significance is less than 5%. So based on that one, we could use that. If you check the quadratic here, I think it's this one. It's not good. They are so far away. But you can have this kind of information. And for example, for your assignment for this week, you have to do the program by Excel or MATLAB. But that could be your analyzing part, adding this one there in your program. What I also wanna point for you is that check from the help what these functions actually are, because otherwise you may misinterpret the function here. So always check the help what they actually are. So as you see, the part of this lecture is quite a short one because it's part, all these are connected to each other. This is just shown for the least squared method because if I have understood correctly, also our professional teachers, so mechanical engineering teachers and civil engineering teachers are familiar with this method and they may require you to use, so you can also practice them. But of course, because you are already familiar with the SPSS, you can use that one. I was attending this morning a MATLAB webinar, and it seems that statistical analysis in MATLAB are also quite excellent. I haven't used them yet, so I cannot give you any practical ideas how to do them, but that is the next step I am trying to learn by myself. So if you find them and you could do this kind of curve fitting and a statistical analysis of them within the MATLAB, it would be marvelous. If you are going to be any kind of designers in mechanical engineering field, MATLAB and this kind of working is probably something you are going to face anyway. You want to ask something? If not, I open your exercise. So you have plenty of time today, and if I were you, I would try to do both of them today, Freddie, and return them. Because I'm going to stay here, I am able to answer your questions and problems. And of course, when you return them, you can get rid of them. So you don't need to think about them anymore. All right.
Excuse me.
Hmm?
About
Yes?
the interpolation and extrapolation. There is a criteria that we should give some kind of comments in this. So what should we give? Like
The comments means that when you are doing the program, you have comments there. For example, that next I am solving this and this. So when somebody else is reading your program, he or she knows what is actually done. Because programming is like handwriting, we all have a different way of doing it.
yes, and when I doing the exercise, I don't know why the exercise one of interpolation is correct, but like in the second one is have minor mistake, but like I don't know what is the issue.
What do you mean by minor mistake?
Like it is not exactly 2.5113, but like 2.515 or something like that.
Do you see what is the word before 2.5?
It's about
This is numerical. They are usually not exactly the same because we use different programs and how they handle the numbers. It may be different. For example, last week I had a big problem with the stack because it said that student's answer was incorrect, although I did know it's correct. And it took 2 hours for me to understand that a stack couldn't get exact value 0 as it should have, but the value was about 0.5 times 10 raised to minus 16. And so it was very close to zero, but it was not exactly zero. So it's about rounding and that kind of things. Somebody asks, should we do both reports? Of course, it's not a must, but I hope that you could do them because it makes your life easier. You don't need to think about them yet, and you still have 1 hour to do them.
And like so we completed it. Does not like do it like a report, but like just put it in function and
Yeah, just a program, and inside the program, some text commenting your programming, and also the analyzing the results.
and just give the uh, Excel file, not PDF file.
Excel, yeah, Excel or MATLAB.
Yes, thank you.